Processor and microcontroller. In this lecture, we will be talking about machine cycles and bus timings. Okay, so first of all, what is a machine cycle? So machine cycle is basically the time duration. Let's write it down. It is the time duration taken to complete one of the following. Okay, which are they? They are memory access, I/O access, input output access, or sending and acknowledgement. Okay, so most of the or all of the basic tasks that has to be done to complete the execution of an instruction are usually categorized into either of these three. Okay, and these are not the classification of machine cycles. There are more number of machine cycles, but you can say, okay, machine cycle is the time taken to complete maybe a memory access or an I/O access or some other purposes, some acknowledgement or sending something like that. Okay, so in this figure you can see that it is noted like there is a fetch cycle, there is an execution cycle, there is an instruction cycle, and these are denoted as machine cycles, right? So and we have given T1, T2 like that. So what are these? So from this you may come to the conclusion that okay, machine cycle is not the only thing, there are something else. Okay, there are something else. Okay, so if you look at here, you can identify that okay, machine fetch cycle is a type of machine cycle, execution cycle is a type of machine cycle, but instruction cycle is not, like it is like a composite of both of these. Similarly, this T1, T2 etc. are smaller divisions. Okay, so from this figure we can identify three things, that is T state, then a machine cycle, and an instruction cycle. Okay, T state, machine cycle, and an instruction cycle. So these T1, T2 etc. they are called T states. That is a single clock cycle. Okay, a single clock cycle of a processor is called as a T states, and a machine cycle is, what is this? The time taken to execute either of these, some of these, memory access, input output, and some other purposes, functions. That is a machine cycles. So obviously for executing a machine cycle, it will require a certain number of times, number of T states. Okay, that is some machine cycle. For example, here if you see machine cycle 2, that is execution cycle in this example, it takes 3 T states, but here the fetch cycle is taking 4 T states. It is just an example. Okay, so machine cycle constitutes of T states, and similarly instruction cycle is a combination of different machine cycles. Okay, that is, it is a time taken to complete execution of instruction. Okay, that is our main purpose, that is execution of instruction. It is subdivided into machine cycles. That is, we are going the other way. The process of execution of an instruction, the time taken for that is called as an instruction cycle, or the processes which is required to be done for executing an instruction is called as an instruction cycle, So instruction cycle, it constitutes of fetch cycle and execution cycle. In some other processors, there can be decode cycle like that. It depends on the processor. Anyway, the takeaway should be that instruction cycle constitutes of different types of machine cycles, and even this execution cycle varies depending on the type of instruction that you are trying to execute. Okay, and each machine cycle, okay, these are just two examples of machine cycle. There can be other machine cycles also. Each machine cycle, depending on what purpose it is doing, what purpose it serves, it constitutes of so many T states. That is, it takes a certain amount of time to do whatever purpose is required. So this is the hierarchy. The smallest division is the T state, which is a single clock cycle. Then machine cycle is there. That is the time required to do a basic, let's say a basic operation. Okay, basic operation, and then these some of these basic operations come together to implement or execute an execution of an instruction. That is called as an instruction cycle. So now let's see these machine cycles in detail. Before that, for 8085, one T state, okay, one T state is 320 nanoseconds. That is 1 by clock frequency. Okay, 320 nanoseconds. Types of machine cycles. Okay, so in 8085, the types of machine cycle can be opcode, fetch. Right, opcode fetch means the opcode, the specific the opcode part of the instruction, it is being fetched from the memory. That cycle, that is a specific cycle, and that is same for any instruction. And the first part of the execution of an instruction is always an opcode fetch. Okay, it is then the execution differs. Right, execution part differs. So there can be a memory read or write, then there can be an input output read or write. Okay, similarly there is the requirement of interrupt acknowledgement. Right, that is whenever the processor is getting an interrupt, the processor has to acknowledge the interrupt. That is INTA, right? Remember, we studied it in the pins, different types of pins. So INTA, for that interrupt acknowledge, that is a separate machine cycle. Then there is hold acknowledge. And then there is a bus idle machine cycle. So these are the different types of machine cycles. So the thing is that none of these alone constitute an instruction cycle. So we'll go through some of them one by one to see how the instructions, the machine cycle works, and how the bus changes, how the different corresponding signals, the values in the pins changes and all. Okay, let's see. Fetch machine cycle. Okay, so this is a diagram of the data and address path. Okay, address bus. So like with this you can see which data is flowing to where, or what address is flowing to where, and this is called as a timing diagram. This is a timing diagram. So what it shows is, it has the clock is there, and it is divided into different T states. Okay, then we have the, so clock is there, then we have the higher upper address bus, then the multiplexed address bar data bus, ALE, the status let's say pins, okay, input output IO bar M bar and S0 and S1. Then depending on the specific process machine cycle here, the extra pins will come here. Since this is an opcode fetch, that is, you have to read something from the memory, right? Therefore here we are showing the read bar pin, right? Okay, so 4 T states are there. The higher address bus will always be the same, right? It won't change till the last part will come here, let it be. But for the main part, it retains the higher order address A8 to 815. Then the lower order, remember it is a multiplexed one. So for the first clock cycle, it acts as the lower part of the lower byte of the address, and for the remaining T states, it acts as the data bus. So, and the ALE is similarly like that. Address latch enable is high for the first clock cycle, and then it becomes low. So that we can see here. Then what is happening? Then after the first clock cycle, that is after the first T state, this AD lines AD0 to AD7, it acts as the data bus. And what is there in the data bus? The opcode that is to be read. That is, we have our 8085 processor here. We have our memory here, and the processor gives the address and it takes back the data, right? Here the data is, it so happens that the data is the opcode. This is how a memory read happens. So similarly, so here the data happens to be the opcode, right? And this is the IO bar M bar and S0 S1 combination for an opcode fetch. Okay, and here see, when the opcode is being loaded into the data bus, then the read pin is enabled, and this is connected to, this is using some logic gates. The read MEM read control signal is generated and given to the memory, right? So this part corresponds to the opcode data path. Okay, and here you can see how the data is flowing, right? From the PC, how the address is coming, program counter, the lower part is coming here and it is latched, and the higher part is coming here, and the combined address is given to the memory, and from there the data bus takes to the instruction register, right? Similar, something like that. Okay. The T4, right? Here if you see, this is given as unspecified. Actually up to here, up to T3, the reading of the opcode is being done. Then the read is complete. Anyway, for any memory read operation, it takes only 3 T states if it is a single byte. So what is the purpose of this fourth T state? It is used for decoding the instruction, right? The instruction has to be decoded, then only the control unit can do something, right? So once the instruction is given to the instruction register, it is decoded and the corresponding data is given to the timing and control unit. That is what is happening in the fourth T state. Now, this is the memory read machine cycle, right? So again, nothing changes here. ALE is initially it is disabled, then it is used. It becomes goes from 1 to 0. Then similarly the lower address bar and data from memory, right? This one. And here the thing to notice is the combination of the IO bar M bar and S1 and S0. Similarly, during this path, that is when the memory is being read, this read pin is enabled. That is to be noted. Similarly, same thing, the address is already given here. Here we are not, yes, the address has to be given. So the address is given here, right, and the latch is used, and the data, it goes through the, it depends where it is being read. Here this is irrelevant, right, because this is not an instruction fetch. So the data doesn't need to go to the instruction register. It can go to, it is going to the accumulator. Okay, that is what is happening in the memory read machine cycle. Memory write machine cycle. Here the opposite thing is happening. Whatever is happening in the address and ALE, these things are the same. So the higher address bit, lower address byte, and from then here it will be data. The thing is that here data is taken from the processor and into the memory. The path changes. Okay, but the address is always from the processor to the memory. It never changes. The flow of data is bidirectional. So earlier it was from the memory to the processor. Now it is from the processor to the memory. Okay, so here also take a note of this, how the status signals change, and also here we are using the write bar signal because the read bar signal is irrelevant here. Here only the write bar signal is required, and we are giving how it changes corresponding to the different T states. Type of machine cycle, which is the IO read machine cycle. So here also the concepts are similar, how the address and data buses change, how the here again, since it is a read, the read signal is changing, and the data is coming from the IO device, and also the status signals are changing. So this is important. If you look at it in most of the timing diagrams, whether it is a read or write, most of the parts are similar, very similar. The details, the fine details are changing, like what address is coming here, what data is coming here, and mainly the status, because the status signals determine what type of operation is actually, what type of machine cycle is actually happening. Okay, so if 110 it is the machine is the status combination for IO read, then you definitely need that combination for IO read, because you cannot have a IO read with 101 or 011 or something like that, because those have other values, and depending on the status signal, the processor functioning and how the peripherals or memory responds to the processor, that will also change. Okay, so take a note of this. The next is IO write machine cycle. Again, same thing, the status changes and this signal changes. Always remember, earlier in here the data transfer was taking place between the memory and the processor. Now in this and the next one, the data transfer is taking place between the processor and the input or output device. Because this is a write, it is an output device. Because this is a read, it is an input device, right? That is a concept. The combination of machine cycles for a restart instruction, right? So basically, restart is an interrupt. Okay. Restart is an interrupt. So this part, okay, you can consider this part to be the response of the processor to what is happening when an interrupt is coming, right? So what is happening, the main takeaway is that we are considering these two signals, the INTR and INTA bar. Okay, so initially we have the PC program counter high and program counter low. Okay, because some sort of instruction is being executed, right? Because when there is an interrupt acknowledged, That means we want to change the execution, change the flow of execution of the instructions, and we want to jump to the interrupt service routine. Okay, so that is happening here. That is, we are loading the we are accessing the PC, and the main thing is that here an interrupt request is coming. Okay, that is there, and here it goes low, but once it is accepted, the INTA, it goes low. That is, it is letting the processor know that okay, the interrupt is being acknowledged. Fine. Then the other two machine cycles are okay, 001, that is a memory write. And what is the purpose here, and what data is, what location is being accessed here? Here the stack is being accessed. Okay, SP-1 and SP-2 is being accessed, and what is being stored here? PCH and PCL. Basically, when an interrupt is coming and it is acknowledged, before going to start the execution, what has to be done? The program counter that we have, okay, it has to be pushed into stack. The current program counter has to be pushed into stack. That is what is happening here. So this is the interrupt acknowledge cycle combined with two memory writes, which is the entire restart instruction, which is an interrupt. Okay, so with this I hope you got an idea regarding the memory cycles, different memory cycles, and how to read them. Okay, how to understand them, how the data flows. Okay, these are basic machine cycles, and with this you can actually try different what do you say, different instruction cycles. You can create, or you can identify, or you can synthesize different instruction cycles by concatenating the machine cycles. For example, you have okay, for example, you have say an operation execution. Let's say you have an add instruction. Okay, so add means first of all you need an opcode fetch, right? Then you need an execute cycle. Okay, and depending on the type of operand, that is whether the operand is in a register or if the operand is in the memory, then there can be an memory read operation in between, right? So what you have to do is you have to first your first machine cycle will be an opcode fetch, then there can be a memory read, and followed by it there can be some other execution part, something like that. So basically what you have to do is you have to concatenate or put one after the other different machine cycles to create an complete instruction cycle. Okay, so with this I am winding up the topic of machine cycle, and after once we have gone through once you go through different instructions and what are the different processes of executing an instruction, you can create the timing diagrams for different instructions. Okay, thank you.